Okay, in this video, we are going to go over Chapter 8. Chapter 8 is a topic on the confidence interval. We switch topics from probability now into a confidence level and hypothesis test. Chapter 9 and rest of the semester will be dealing with hypothesis test, and chapter 8 is like a prereq for chapter 9. So the idea that we talked about in chapter 8 will carry on to chapter 9 and on. So what is the purpose of this chapter? This chapter is to estimate the entire population parameter, like a population mean value or population proportion with sample data. Recall in chapter 1, I mentioned the difference between the sample and a population. A good sample should project accurate information about entire population. That was the whole purpose of selecting a sample in a good way, because it's impossible to gather all the data of entire population. So that's what we are doing. We are gonna have some kind of a sample data value, use that data value to predict the population value. So for example, one can gather the data of 1,000 sample to see the average weight of US adults. And with that data, we are going to estimate the entire population average weight of US adults with some error bound. Okay, so let's begin with terms and definition, and then we'll look at some of the example problems. First one, a blank is a single value or point used to approximate a population parameter. We call it point estimate. A blank confidence interval is a range or interval of a value used to estimate the true value of a population. So another word for point estimate is your sample value, like sample mean, sample proportion. And the confidence interval is like a range of a value. So we say, the average weight of US adults of 1,000 sample was 130 pounds. I'm just making a number. Then we are going to use that. So my entire population will be about between 120 to 140 pounds. We cannot really say it's exactly going to be 130 for the entire population because, of course, there's more people in the population. So we build this range interval. Sample of 1,000, we got 130 pounds. But the entire population should be around 120 to 140. So we are kind of we are giving a little bit of a lenient way to estimate the entire population value. And here's the second part. We can use the sample proportion to construct a confidence interval, estimate true value of a population proportion, and we should know how to construct and interpret such confidence interval. And that's what we are going to do. That 130 should be somewhere in your estimation because your sample is a good prediction of a population. So we are gonna subtract some values, and that value is we call it error bound. So we are gonna say 130 with the 10 pounds up, 10 pounds down or 10 pounds up. So that is called the error bound. The blank confidence level is the probability 1 minus alpha, such as when we say 95% confidence interval, that means we are 95% confident that this answer is correct with the 5% inaccuracy. So we call that 5% inaccuracy an alpha value. So I can say, I have 130 pounds as my sample. My population average weight should be around 120 to 140 with 95% confidence. We don't really have that 100% confidence because you really cannot say 100% because you didn't technically get all the entire population data. So the most common confidence level is a 90%, 95, and 99, which makes the alpha value, which is uncertainty, the 10% inaccuracy, 5% inaccuracy, and then 1% inaccuracy. The last one, critical value, is the number on the borderline separating sample statistics that are likely to occur from those that are unlikely. So basically this part right here, likely to occur with unlikely. The number, and this is the notation, we call it Z with the alpha over 2, is the critical value, deals with the z-score. Recall that z-score comes from the normal distribution with the property that separates an area of alpha over 2 in the right tail of the standard normal distribution. Now this term has a lot of information. We have the number notation z alpha over 2. It's a z-score. And then what does it mean separates the area alpha over 2 right tail of the standard normal distribution? So here, next example 1 illustrates how to find the confidence interval and interpretation. So I'm going to jump right onto example 1 and then work on the problem to find the critical value and go back to the definition to re-explain. Okay. Find the critical value z alpha over 2 corresponding to the 95% confidence level. Well, let's use all the notation. We have the confidence level 95%. That means we have alpha value 0.05. So 95% confidence level mean we have an alpha value 0.05. And you see the notation alpha over 2 right there. So I want to take the half value. Alpha over 2 will be 0.05. Oops. Divided by 2, which makes it 0.025. What does that mean? That means we have the standard normal distribution. Standard normal distribution, recall that it has a bell-shaped curve, right? With this means bell shape with mean 0 and standard deviation 1, right? So this is what's going on. We have this distribution, 95% mean. I'm now looking at this as a middle value, 0.95, the middle area. The confidence level is middle area. Why? Going back to this definition here, when we build a confidence interval, we start with our mean, which is in the center, and then we add, subtract a little bit. Range, create a range. So we look at the middle, not from the lower or upper. We looked at with the middle because that's where our sample mean is, and then add, subtract. That's why we are dividing the region from middle and on. Alpha value is 0.05, but technically there's two regions, left tail and right tail, and that's what this means, area of alpha over 2 of the right. So alpha over 2 is 0.025. So this area represents 0.025. This area represents 0.025. So the corresponding z-score is this value here. That when it says find the critical value, that z alpha over 2, I'm looking for that value right there. Okay, so how do we find that? It's a z-score. We have done this before, finding the x value. So that will be inverse norm. Inverse norm, area to the left. Area to the left here is 0.95 plus 0.025. So you will use 0.975. And then standard normal distribution has a mean 0, standard deviation 1. So you put 0, 1, put that on the calculator, I get 1.96. Okay, so that's what critical value is. So I'm going to actually create another column called critical value, because we will be using critical value to build confidence interval, and then write it over here. So we got the 95% as 1.96. Let's also find the 90 and 99 because those are the most common. So let's get all the critical value in one page so I don't have to do inverse norm all the time. Now to find the 90%, then your area will be 0.05. So the 90% now is this one. So the half area is 0.10 and then 0.10. So for the 90%, you're going to have z alpha over 2 as inverse norm. Alpha is 0.10, so it should be 0.05 because we are dividing by half. So just like this. So you have 0.05. 0.05, so you're gonna have 0.95, 0, 1. My critical value, I'm getting rounding 1.645. So let's put it there, 1.645. And then last one, let's try the last one too. If this your area is 99, you have an inaccuracy of 0.1. That's the whole two tail combined. So half of that will be 0.01 divided by 2, 0.005. 0.005. So your z alpha over 2, your critical value will be inverse norm. Area to the left will be combined of these two, 0.99 plus 0.005. I have 0.995, 0, 1. Put it on the calculator. I'm getting the z-score of 2.576. 2.576. You can see that as we grab more area, your value will get bigger. Remember, this was 1.96. 2.5 is here, so your range is getting bigger. So you're grabbing more numbers, so you have more accuracy because your interval is more larger number. Okay, now let's do this part here, actually building the confidence interval. Before we do that, I have to give you the formula of how to create the confidence level. Now, estimating population mean, the first case is we're going to start with estimating the mean, average. Population mean when sigma is given. Sigma is a population standard deviation. So you have to determine whether you know the population standard deviation or you don't know population standard deviation. If you have a population standard deviation given, if population standard deviation is known, we use the normal distribution curve. Now, this is a little bit later. Sometimes the problem may not give you population standard deviation. That's 8.2. Estimating population mean when sigma is unknown, then we are going to use not a normal distribution because we don't know the sigma. We will be using student t distribution, and I'll explain what that means in 8.2. So just note that determining which distribution to work on, you have to know whether you are dealing with the sigma or whether you know the sigma value or not know the sigma value. Okay, so requirement, how do we construct the confidence level estimating population mean? Well, first, your sample should be selected in a simple random sample. So select good method, using the good method. And then you either or both of this condition is satisfied, the population is normally distributed, or you have a large enough sample. which is greater than 30. So your confidence level that 120 to 140 pounds is a formula of basically your sample mean minus some error bound for the mean value, and then you add some error bound for the mean. What is an error bound for the mean? How do we calculate it? There's two ways to calculate it. First one by formula. EBM is calculated using your critical value z alpha over 2 times sigma over square root of n. This one was your recall in chapter 7 on central limit theorem. This was your sigma x bar, the mean, right? Second way is you can also find the confidence error bound using a calculator. So on calculator, let me write it over here. On calculator, you can actually use both of them. It will give you both. Stat, test, and then z int. Okay, I'll show you. I'm not going to be using the formula. I will still give you the formula, but I'm going to be using the calculator to calculate all these because it's a lot faster. Also, if you know the confidence interval, EBM can be found by upper confidence limit, CI, confidence interval limit, which is this number here, this number. That's your upper confidence limit. So let me underline. So this part minus lower confidence limit all over 2. Okay, so you take these two numbers, subtract, divide by 2 will also give you EBM. So let's try example 2, which is your first homework problems. Suppose that an accounting firm does a study to determine the time needed to complete one person's tax forms. It randomly surveys 125 people. Okay, so that's your sample size, 120 people. So that's part A, 125N. Sample mean, that's your X bar, 23.7. And the population standard deviation, notice the word population standard deviation. That's a sigma, not S. So sigma is given 6.2. The population is normally distributed. So population distribution is normal. So we can actually use our z interval calculator function to calculate all the requirements satisfied. Take a look. We have a sigma known right there. We have a population is a normal. We have a sample size larger than 30. So I can construct a confidence interval using the z int. In words, define what x and x bar is. X was the variable. X bar is the average. So we have first one, x bar is the time needed. Well, first x bar has to do with the mean. I don't see the word mean, so I can already eliminate this one. I don't see the word mean somewhere. And then x is the mean. That's not true. It should be the other way. So I can also eliminate the second one too. X bar should have a word mean, but this one has mean with x. So third one, fourth one, x is the number of tax form that accounting firm completes. X bar is the number of mean number of tax form. Well, we have sample mean is given as an hours, right? Sample mean is 23.7. So sample mean should have a time involved. It has a number. but we have a mean as a time, as a unit. So the last one will be the correct one. Okay. X bar is going to be, what is it? Sigma is known. We are going to deal with standard normal distribution. So this will be the normal distribution. So for the normal distribution, recall chapter, this is your CLT, in fact, number 1, X bar. CLT number 2 was the sum. So this is your mean of X bar. This is your sigma of X bar, which is sigma over square root of n. So mean of X bar is just your mean value. So mean value. So your mean is given as 23.7. Sigma of X bar is sigma, I know that's 6.2 divided by square root of 125. It says rounded to the 2 decimal place, rounding 0.55. Okay. Explain your choice. I'm going to eliminate top 2 because I didn't even teach you what the student t distribution is. It is a standard normal distribution because population standard deviation is known. That was the whole purpose. If population standard deviation is known, we use standard normal distribution. All right, next part is actually calculating this. So they give you this graph to help you visualize. So this part D is this combination with calculating the critical value and then also finding this range number. Okay, so let's start filling out. We know construct a 90% confidence interval. Okay, there's my confidence interval. We want it with the 90% confidence level. That means that goes 90% here. So alpha value is 0.10. So alpha over 2 should be 0.05 each. So 0.05 here, 0.05. And we are actually going to find that number. That number is your confidence interval. So how do we construct that? So the calculator stat test z int. Okay, it's our first time doing it, so I will show you using a calculator and where you can find. So here's our calculator. I told you that it's a stat key over here. So stat key right over here, stat. And then you're gonna go arrow to the right to go to test. And then we are not on the hypothesis test yet. We'll be using the word that says test with chapter 9. But we are building an interval right now. So there's your z interval right there. So number 7. And then if you press number 7, it's gonna ask 2 option data and statistic. You're given statistical value, not the actual list of data. So switch to the stats and then enter. And we have to enter that. That's from part A. Part A, we had a sigma known as a 6.2. So write that down or type it in. It was a 6.2. X bar was 23.7. And then sample size of, it was how many? 125. And then C level is your confidence level. Confidence level, they wanted you to use a 90%. So your calculator will always set it as a 95, but just change to 90 and calculate, and that's it. So you just, your sample value, the average mean time needed to complete text form of 125 customer was 23.7 hours. So if we took entire population, it should take around 22.788 hour to 24.612. That's what it means. So you're using this mean value and then building the confidence interval to estimate the whole entire population set. Okay. All right. So now let's go back and finish the rest of them. The confidence interval rounded to the 2 decimal place, we have 22.79. So you have 24.61. Okay. So that's where the number goes to. It should be around 22.79 hours to 24.61. Calculate the error bound. Error bound, you can use this first formula, but since we already construct the confidence interval, I'm just going to use upper subtract lower divided by 2. So error bound for the mean is upper, which is 24.61 minus lower 22.79 divided by 2. (1.82) divided by 2, I'm getting 0.91, rounding to the 2 decimal place. Okay, so that's it. That is the entire process of building a confidence level. Okay. And we'll repeat this concept in chapter 8.2 and 8.3, but just switching from the mean with sigma known to sigma unknown, and then the parameters switch from mean to proportion. The last part is determining the sample size. If you want to collect a sample to be used to estimate population mean, how many sample value do we need? So remember, we need to have some large enough sample, right? I mean, if you gather the data and then let's say you only had 3 sample value, well, it's not really accurate because with 3 sample, it's too small. So one can ask, how large should my sample size be in order to have some accuracy? And that's fine. And this is the formula of how to calculate that sample size. N, sample size, should be calculated as your critical value. So depending how accurate, 90%, 95, 99, so it switches, times the population standard deviation divided by error bound for the mean, whole thing square. If computed sample size is not a whole number, we are going to round up to the next larger integer because we like to count the sample as a whole body. So let's take a look. Assume that we want to estimate the mean IQ score for the population of statistics students. How many statistics students must be randomly selected for IQ if we want 95% confident that the sample mean is within 3 IQ points of the population mean? Use standard deviation of 15 for IQ score. All right, so what do we know? We know 95% confident level. So Z alpha over 2, the critical value, because we need to calculate it, because the formula is right here. Okay. So we need to calculate the Z alpha over 2, but we already did that in the first page. Right here, 95% has a critical value 1.96 right there. Sigma is given, standard deviation 15. Error bound, this is your error bound point. Within, when we say something is within that point, that means go 3 below or 3 above. So 3 is your error bound number. Using the calculator, I got 96.04, but this is a decimal number, so we round up to the next large integer. You need minimum of 97 sample to accurately predict your entire population mean with the 95% confidence level. Okay. So what happens if sigma is not known? Here on first example, population standard deviation is given. Sometimes you might not know your population standard deviation, so take a look. 6 different national brands of chocolate chip cookie were randomly selected at supermarket, and there's a list of data. I don't know the population standard deviation. So when the population standard deviation is not known, we cannot use a normal distribution because it's not the same. So we are going to be using a new distribution called student t distribution. So I want to talk about the student t distribution a little bit. What is a student t distribution? The student t distribution is developed by William Gossett in 1908. When do we use it? When we have standard deviation not known, okay, and then sample size small. Okay, in the past it was a bigger than 30. Now you have a smaller sample size. So take a look. You have only 1, 2, 3, 4, 5, 6 samples. So that's when we use student t distribution. Some of the property about the student t distribution is it still looks kind of like a normal distribution but flatter. So here's a comparison. This first curve is a normal distribution right there. Student t distribution will still follow that kind of symmetry, little bit of a bell shape, but flatter. Okay, because it's still a curve, you can say area under this t distribution, the whole thing will represent probability will equal to 100%. Shape of a curve depends on the degree of freedom. What is a degree of freedom? Basically, a sample size take away one data value. So if we have, it's not listed over here, but as the shape of a curve depends on degree of freedom. So the shape of the t distribution as the sample size gets larger, the shape of t distribution will look more like a normal distribution. Okay. I'd like to write that down over here. Another property is as n increases, n, which is a sample size, t distribution will look more like a normal distribution. Because it's like a normal distribution, the idea is still same thing. We have a critical value, but instead of z, we use a t because the variable is t. To calculate the t value, the formula is x bar minus mu s over square root of n. And you have calculator function where you can use to calculate this as well. On calc, you can go to, we use inverse norm to calculate the critical z value, right? Inverse norm. So the name kind of follows the same thing too. It's called inverse t. area to the left, and then you put degree of freedom value. Just the two number. What is a degree of freedom? Sample size subtract 1. So let's do a little bit of a practice problem calculating the critical value. Now, I'd like to say something about using the calculator function. If you have TI-84, you're fine. You have an inverse T. However, 83 do not have inverse T function. You have inverse norm, but you do not have an inverse T. So I'm going to show you alternate ways without a calculator to calculate the T distribution, which is using the formula, or even easier one, critical T value chart. Okay, because if you just look at the chart, it will tell you the number. Okay, so let's do this one. A sample size n equal 12, which is smaller than 30. So you know that I'm going to be dealing with student T distribution, and you don't know what the population standard deviation is. Sigma is unknown. Oh, found a mistake on here. This should be a sigma, not S. Because S is a sample standard deviation. Sample you know, because you are given the sample value, but not the population standard deviation. So make a note, typo. So on here, I don't know. The only thing I know is n equal 12, and that's it. Okay, so let's build a critical value. 95%. So I'm going to draw a little bit of a flatter curve because it's a T distribution. Still, same idea, 0.95 should be in the middle, so that represents 95% confidence level means alpha value 0.05, so each tail has 0.025, 0.025, 0.025, so you have to calculate this right over here, T distribution 0.025, I will use inverse T. Area to the left will be 0.95 plus 0.025, so 0.975. Degree of freedom will be 11. Do not use a 0 and 1. That's inverse norm setup. This is inverse T. So inverse T has this setup, only the two value. Let's check. So I'm going to pull out the calculator and show you how to enter that. Okay. Let me clear. Okay, inverse T is you can find this same screen as inverse norms. The second bars to get to the distribution. Inverse norm, inverse T. 83 do not have this one over here. So I will show you other way to do it. So number 4, inverse T. Area, always the left value. So 0.975. DF is a degree of freedom. Sample size minus 1. Sample size was 12. Subtract 1 will give you 11. Paste. Your critical value is, I'll just round it to the 3 decimal place, 2.201. 2.201. So how else can you get this if you do not have a calculator? I uploaded a critical T value chart on Canvas module. So open up the critical T value chart, and then you just have to look at the two value, just like you need an area to the left and degree of freedom. So you look at that. Left-hand column, you have the degree of freedom. Degree of freedom was 11. So you look at the 11 right there. Okay, and then area in one tail, two tail, that means area in one tail is the combined alpha value. Area in two tail is alpha over 2. So either way works. You can look at it either way. We had alpha value 0.05 or 0.025. 0.05, 0.025. Okay, so oh, I'm sorry, area in one tail is alpha over 2 because it's just one area, so it should be smaller. So this is alpha over 2. This is alpha. So I switch it around. Let me write it more clearly. Because the area one tail, it's just one number. Alpha over 2. Oh, let me erase. Alpha over 2, alpha. We had alpha value 0.05, 0.025. So which is right here in the middle column. So you look at the cross section, which is equal to 2.201. So reading the chart is not that bad too. It's pretty fast. And you get the same result, 2.201. Okay. Now let's build a confidence interval. So few things, I'll give you the formula, but also I'm going to be using the calculator to construct the interval. It should be pretty quick. Chapter 8 has all the calculator functions, so it's nice. You don't really have to use the formula. We have to make sure before we begin, your sample is picked randomly. Verify that either both or both of this condition is satisfied. The population is normally distributed or n greater than 30. Sigma is unknown, right? That's the important key point. Sigma unknown, we use t-distribution. EBM, the margin of error is, because it's a t-distribution, don't use z alpha over 2. You have t alpha over 2, and then you have s over square root of n. S is a sample standard deviation. And then to build that, you're going to be having x minus EBM, x plus EBM. On calc, the name looks really similar. Remember the name was zint? Now it's tint. Stat, test, and we are going to go into tint. Okay. All right. Another thing, if confidence interval is known, just like we did it, you can find EBM by subtracting this part here, upper limit minus lower limit divided by 2. Divided by 2. Okay, all right. So let's try the next one. 6 different national brands of chocolate chip cookie were randomly selected at a supermarket. The grams of fat servings are as follow: 8, 8, 10, 6, 9, 9. Assume the underlying distribution is approximately normal. All right, so underlying distribution means like your sample distribution. Okay, but we are doing the population distribution. So one thing, the problem on the test or homework will not tell you, oh, this is a normal distribution or this is a t-distribution. You have to determine. The big thing that separates from normal to t is sigma. So look for sigma. Do I have sigma known or is sigma unknown? Population standard deviation anywhere in the sentence, I don't see that. You don't see the word population standard deviation anywhere here. So this is a t-distribution. Okay. Since sigma is unknown, this is t-distribution. Okay. So let's build 90% confidence interval. All right, so we have a 90%, so that's my area in the middle. So alpha value will be 10%, so one tail will be half of them, so 0.05 here, and then 0.05 here. We build a confidence interval, enter that, and then find the error bound. Let's do that using a calculator. Just like we did it with the z-int, you're gonna do it with t-int. Okay, so stat test t-int number 8. This time you are given the list of data, so you're going to be putting in data and enter. Now where the calculator do not have those 6 chocolate chip cookie data values, right? So you have to let the calculator know those 6 data. So you have to create a list and store that data in L1. You see that L1. So where was L1? L1 was stat edit L1. So let's enter that. It was a 8, 8, 10, 6, 9, 9. 8, 8, 10, 6, 9, 9. So we enter that. And then let's go back. Stat, test, t interval. Frequency, keep it as a 1. Frequency means count. We enter those already by itself. 1 time, 1 time, 1 time, 6 times. So just keep it as a 1. If you keep it as 2, you're gonna double the data, what you enter. Confidence level, we wanted to build it with the 90%, yes. And then calculate. There's your interval. 7.21 to 9.46 rounded to the 2 decimal place. Okay. 7.21 and then 9.46 rounded to the 2 decimal place. If you have TI-83, you might not have a T interval as well because you do not have a T inverse T. If that's the case, you just have to use the formula. How do you use the formula to do that? It's right over here. Okay, so I will show you how to do that. Here, you have to know your sample mean value. Where's my sample mean? Sample mean is easy. How do you do this? Add all these divided by 6, right? So let me do it by hand and show you that you're gonna get the same way too. Okay, and we'll do part 3. So if you do by hand, let's first calculate x bar. So the formula is x bar minus EBM, x bar plus EBM. X bar is 8 plus 8 plus 10 plus 6 plus 9 plus 9 divided by 6. So 8, 8, 10, 6, 9, 9 divided by 6. I am getting 8.3 repeated. I'll keep it as a 50 over 6. I don't want to round it too much. EBM, how do we calculate EBM? You do not have a EBM can be calculated here. Here's the formula. Critical value T alpha over 2. S over square root of n. T alpha over 2. How do we calculate T alpha over 2? That's the critical value. We had done this with the 95. So now it is 90%. So you're looking at the T value chart. Your degree of freedom now is, so let's erase all this so it doesn't get confused. You have a 6 data. Now you are dealing with 5 because n minus 1. And your alpha value, so it was a 90%, right? Confidence level. So alpha value is 0.10. So alpha over 2 is 0.10 divided by 2, which is 0.05, which is this column here. So looks like my critical value is 2.015. S over n, square root of n, that's square root of 6. S is a sample standard deviation. Sample standard deviation we use, remember, one-var statistics, right? Recall one-var statistic. So I'm gonna do that here. We already entered in L1. Remember, stat, edit, there was a data. So standard deviation is a messy formula. So I show you in chapter 2. You can do this by using the stat, calc, one-var statistic. Yep, there's L1. Calculate. There's your S. 1.366. I'll just keep it as of 3 decimal place. 1.366. Okay. So my error bound is, this was 8.3 repeated. So pulling the calculator, 2.015 times 1.366 divided by square root of 6. I get 1.1237, rounding to the 4 decimal place, 1.1237, okay? So your confidence level will be 8.3 plus 1.1237, 8.333, subtract 1.1237. Should be 7.21, 9.16 when you round it. So let's check it. 8.333 plus, oops, I switch it around. Since you have a lower limit first, let's do that as well. This one here should be minus. And this should be plus. Minus 1.1237. 7.2093. Upper limit 8.333 at 1.1237, which is 9.4567. But if you round it to the 2 decimal place, I'm getting exactly the same number, 7.21, comma 9.46. So there you go. So either way, if you do not have a T int or inverse T, do not panic. You have to use the formula. Unfortunately, you have to use the formula, okay? Now, error bound, we actually did it by hand. It's here, 1.1237. Rounding to the 2 decimal place, it should be 1.12. Well, but I show you that if you know the confidence interval, you can do upper minus lower divided by 2. So let's just check if we do get 1.12 using this formula too. Upper, which is upper 9.46, take away 7.21 divided by 2. 9.46, take away 7.21 divided by 2. I'm getting 1.125 right there, rounding to the 2 decimal place. Okay. All right. That's the end of 9.8.2, and we will move on to our last section of chapter 3, which is estimating a population proportion. Your parameter is not a mean anymore, it's proportion. When do we see the word proportion, the P? Back in chapter 4. So you're going to see some of the things that we did it in binomial distribution. Remember P and Q, binomial distribution? Okay. So the underlying distribution is a binomial, and we'll use that to modify the p-hat distribution. So just like we have built confidence interval using EBM, now we have an error bound for the proportion. That is calculated as z alpha over 2 square root of p q divided by n. Now, you can see that I'm using critical value z-score, so you can estimate, you can see that this is dealing with the normal distribution. So we have a population proportion as a normal distribution. So student t distribution is only when sigma is unknown and dealing with the mean. To build a confidence interval, it will be p hat, the sample value, minus EBP, and then p hat plus EBP. Okay. All right. Note the underlying distribution is a binomial distribution. And then recall that p hat was calculated as x over n, right? Probability of success. But we will follow a normal distribution. Okay. So a little bit of a connection. Binomial. The way we wrote was NP, right? That was your mean value, and then standard deviation was NPQ, right? Because since p hat follows normal distribution, we need to calculate the mean and then standard deviation. The mean was calculated as NP, and then standard deviation is NPQ. But it's technically not X we are dealing with. We are dealing with p hat. What is p hat defined as? That's basically X over N. So I have all the X set up here. You see that X is defined, X is defined as NP, NPQ. So I just have to modify this by, how do we have the p hat? Just divide by n. So wherever you see here, you have NP, just divide by n to match that up. NPQ divided by n. And this will be useful when we define the notation right here in part B. Okay, right there. Right? So that's how you calculate the mean and the standard deviation. So I'll write it over here. So let's try that. So p hat, following that, is n. Your first number is NP divided by n, and PQ divided by n. So let's go through and then read what n value and p value and q value is. A telephone a telephone poll of 1,000 adults. Oh, there's your sample size. 1,000 of adult American was reported in a magazine. One of the questions asked was, what is the main problem facing the country? Suppose 16 people answer crime. Remember, binomial was 2 cases. Success, failure, 2 categories. So 16% answer crime. So there's your P, 16. So what is my Q? The complement, 1 take away 0.16, which is 0.84. Okay, so if you forgot some of the terminology or some of the variable, go back to chapter 4. We talked about NPQ. So N1000, P 0.16, and then Q 0.84. So let's put that. So your N mu is NP over N. So 1000 times 0.16 divided by 1000. Cancel that. It's just 0.16. Okay. Sigma is square root of N 1000 P 0.16 Q 0.84 all over N, the 1000. It's asking you to round it to the 3 decimal place. I'm getting in a calculator 0.012. Explain your choice. It's not a student. I can eliminate this one for sure because we are not dealing with the t distribution. We are dealing with the proportion. So standard normal distribution. We know that p hat deals with, as I mentioned right over here, underlying distribution is a binomial, but p hat follows a normal distribution. So it's not a your x is a binomial, not p hat. So this one right over here. This part I didn't say anything about NPQ greater than 10. There was not, that one is a random fact, not given on the note. So the best one is the last one. Let's build a confidence interval. We have a formula to do a confidence interval, which is right over here, follows the same structure as x bar minus EBM EBP. But also we do, fortunately, both 83 and 84 have a calculator function. So I'll be using the calculator function. So on calculator, this can be found by using stat calc. The name is 1 prop z int. Now the name tells you the information. 1 because one set of data. Later on we deal with 2 sets, so there's 1. Prop stands for proportion. Z distribution, normal z, and then we are constructing the int. So the name looks funny, 1 prop z int, but that's how you kind of match up. Proportion is a z distribution. Proportion, z distribution. So let's use 1 prop z int to construct the confidence interval. You can find the same thing on stat test 1 prop z int. So we need to go down. 1 prop z int, letter A. X was, where's the X? Remember, X was given as P hat was X over N, right? So let's go back and then calculate the number. Remember, P hat is given as X over P. We already know what P hat is. It was 0.16. So I have to do some little bit of a work. 0.16, X is unknown, but I know the sample size is 1,000. So how do we solve for X? Multiply 1,000 multiply 1000. So you have 0.16 times 1000. We have x equal to 160. In other words, 160 divided by 1000 will give you 0.16. So that's your x, and then n will be 1000 that you're going to put it in a calculator. X was 160. N is 1000. The problem asks you to construct it with the 95%. Calculate. Yep, that's what I have. Rounding to the 4 decimal place, 0.1373, 0.1827. Point 1373, 0.1827. The confidence level was 95%. So that makes the 5% inaccuracy, but dividing by 2, we each get 0.025. The one prop z-test said 1.1373, 0.1827. How do we calculate error bound? Upper minus lower divided by 2, just like we did it with previous 2 section. Rounding to the 4 decimal place, I'm getting 0.0227. Okay? All right, last part is determining sample size. We did it with the mean, but what if you have a proportion? The formula is z alpha over 2, your critical value, square p hat q hat divided by EBP whole thing square. If, again, same thing, round up if it is a decimal, because we like to count as a whole number part. And then another thing is, sometimes your p hat is not known, then use 50%. We'll just say half-half. Half percent success, half failure. Okay? But if p hat is given on the problem, use that number. Gap, Banana Republic, J.Crew, and American Online are just a few of many companies interested in knowing the percentage of adults who buy clothing online. How many adults, so that's calculating the sample size in order to be 95% confident that the sample percentage, so you see the word percentage, that's dealing with the P, proportion, is error by no more than 3%. Use the result from Census Bureau, 66% of adults buy clothing online. So let's do some work. 95% confidence level. Let's calculate our z alpha over 2, which we did it at the beginning. 95%. We have z alpha over 2, 1.96. What else do we have to know? So n, you have 1.96 square. P hat, do I know P hat? Yes, 66. So what is Q hat then? 1 take away 0.66, which is equal to 0.34. 0.66, 0.34. Your error bound, error no more than 3%. So your EBP is that 3%, but it's a percentage, so we have to change to the value 0.03. So don't forget, you should have 0.03 square. Putting in a calculator, I'm getting 957.839. That's a decimal. Rounding to the whole number, I get 958 as a final answer. Okay, that's it for chapter 8.